On the 5th of December 2022, the US National Ignition Facility achieved one of the most anticipated breakthroughs we have ever seen for nuclear fusion. The breakthrough was that for the first time in history, more energy was released from a fusion reaction than went into the fuel. In this video, we'll explore how they did it, what this breakthrough really means, and the limitations that it has. Before getting into the details of the recent findings by the National Ignition Facility, we can first see what they did in practice to give it some more context. The aim of the experiment was to fuse the hydrogen isotopes deuterium and tritium, which are the fuels, so that they release energy. This energy is released because the product of fusing deuterium and tritium is helium-4, which is lower in mass. Because there is a difference in atomic mass between the input fuel and the output, energy is released, as energy is equal to mass times the speed of light squared. As the speed of light is an extremely large number, a small change in mass results in a large release of energy. However, getting these atoms to fuse is not easy, as it requires a huge amount of energy. This energy is used by scientists to create extremely high pressure and high temperature environments for the fuels, as it makes the fusion of atoms much more likely. There are a number of ways to get the fuels to the required conditions. However, the National Ignition Facility uses a method called Inertial Confinement Fusion. For this, they use the world's most powerful laser as an energy source, which is aimed at the small fusion target. The first step in the laser process is the formation of a single beam of light. This beam is then amplified and split multiple times to create parallel beams with higher energy levels. After many stages of splitting and amplification, the final output is 192 laser beams that all hit the target at the same time from different directions. Before being fired towards the target, the light is converted from infrared to ultraviolet, as UV light is better at heating. So now we know how energy is delivered to the target, we can see what the target actually looks like and what happens to it. The target at the National Ignition Facility is truly a piece of engineering genius. It starts with the outer cylinder, known as a hohlraum. When the UV lights from the lasers enter the hohlraum, they are re-emitted as even higher frequency X-rays, which are evenly distributed into a fuel pellet, which is inside. The fuel pellet is a small sphere that is around 2 millimeters across. It consists of a small outer layer of plastic that contains the deuterium and tritium fuel. Some of this fuel is in a cryogenically frozen layer, and the rest is in a gas in the middle. Once the X-rays hit the fuel pellet, the plastic layer implodes at 220 miles per second, causing the fuel to reach densities 300 billion times greater than the Earth's atmosphere at over 100 million degrees. In the hottest and most compressed part of the fuel, fusion then takes place, and in turn begins to ignite the rest of the fuel through a burn wave. Once the burn wave has finished, the hope is that the fusion reactions have released more energy than it took to get them to start, which is kind of what happened during the breakthrough experiment at the National Ignition Facility on the 5th of December 2022. However, now we understand the whole process, we can understand what this net energy breakthrough really means. One of the key outcomes of the net fusion energy experiment was that the fusion fuel reached ignition. This means that the energy lost due to things like radiation and conduction were less than the energy being released by the fusion reactions. This is what we consider a self-sustaining burn, and it is what allows that burn wave to spread through the fuel pellet. Although this was notable, it had been achieved before at the same reactor in 2021, and as far back as the 1980s in a less controlled manner using radiation from a nuclear weapon. What was really making the headlines though is the net energy production from the reaction. The reason that I said the breakthrough experiment kind of released more energy than it took to make it happen is because it depends on the criteria that you're looking at. The reports that state the reaction generated 1.5 times the input energy are referring to the input energy from those ultraviolet laser beams compared to the energy released from the fusion reaction. This ratio is known as the scientific Q value. The possibly obvious issue many people have with the scientific Q value is that we want net energy from a whole power plant, not just from the specific reactions inside the reactor. The biggest setback in efficiency is the losses in the laser system. In fact, for the laser system used in the net energy breakthrough, only 0.5% of the overall input energy makes it to the UV laser beams. This value is known as the wall plug efficiency. However, these lasers are running on old technology, and new lasers are much more efficient, with lasers now reaching 20% efficiency. Other large losses happen when we try and convert energy from the nuclear reaction to electricity for the grid. The method for this involves capturing thermal energy from the reaction and using it to heat steam that drives a steam turbine, which in turn spins an electric generator. This process is pretty well understood and has an efficiency of around 30 to 40%. Therefore, when we consider all of the losses when generating the laser beam, converting the heat into electricity, and other energy consumptions from things such as cooling, it is expected we'll need a scientific Q value nearer 15, or 10 times the current value. As a side note, it is also possible to directly capture energy from the changing magnetic fields of the fusion explosion, which would be much more efficient. But when using tritium and deuterium, you can only capture 20% of the output energy using this method, and it generally seems to be less favoured from what I've seen. The other big issue is that even if the overall reactor system can reach a net electricity output, the electricity needs to be cost effective. This is dependent on many things outside of just the fusion reaction, such as the frequency at which we can get these reactions to take place. A paper from around 50 years ago, which still proves very useful to this day, estimates that if 100 pellets of fuel are exploded per second, each releasing 50 megajoules of energy, a scientific Q value of 50 can make the process economical. However, this assumes lasers with 10% efficiency, so we may actually need a slightly lower scientific Q value using modern lasers. To put this into perspective, the net energy breakthrough shot released around 3 megajoules of energy versus that 50 megajoules we mentioned earlier. The laser also currently takes hours to cool before it can be used again, and the fuel pellets are difficult and expensive to make. Although this may seem disheartening, there are some developments that can help. With upgraded lasers being the first obvious improvement due to their high efficiencies and ability to fire more frequently, a second one is larger fuel pellets that can release more energy. This is, however, not currently possible at the National Ignition Facility, as their reactor setup would be unable to withstand the explosive forces. Also, although the facility achieved ignition, which enabled the burn wave to travel through the fuel pellet, it was actually still only able to burn a small amount of the total fuel. This is because the speed at which some of the fuel exploded out was faster than the burn wave that tried to heat it for fusion. Therefore, small increases in the amount of fuel burnt will result in large improvements in the scientific Q value. Although the direct scientific benefits of the net energy breakthrough are significant on their own, I personally think one of the biggest benefits will be in the increased interest and funding that many fusion projects will see, such as ITER and Helion Energy, among others. If you're still watching, please subscribe to the channel, as you must have found this video somewhat interesting, and I think you might like my other videos and live streams I'm now doing related to each video. In the meantime, you can also watch this video on how Google are helping solve another one of nuclear fusion's big challenges.